rainfall in Taiwan, Chinese Taipei. The subject is changing from previous more climate sense to daily weather forecast. I think that's providing to emergency operation. I will not go into the detail as I know most of you are not in meteorology. What I like to try to show you is probably the similar activity has been taken in your home economies. And also I like to show you some of the error or the uncertainty come with the forecast error, the forecast product. I think you have to know the uncertainty if you like to best use of the products. And certainly I would like to have your suggestions to improve our forecast. And this is a quite good countryside view. This is a rice farm in the east side of Taiwan. But if a typhoon invaded this, I think the farmer can face very serious losses. Some of the losses cannot be avoided even you know the forecast a few days earlier, but some of the losses can be reduced if have good preparation. A little bit background for you if you're not quite familiar with Taiwan. It's a small island somewhere here in between of the maybe Manila here to Korea and in east of China. The size is smaller than a typhoon body. And the topography probably is a very interesting one. We have the Central Mountain in center of Taiwan. The about 1/3 of area, the topography high is higher than 1,000 meters. Some of the peaks are higher than 3,000 meters. Therefore, they are very strong orographic forcing for the weather. And in Taiwan, the severe weather are mainly from late spring. We call May. We have very heavy rainfall from the stationary front. And the typhoon, as here, there are two typhoons nearby Taiwan. They will bring a very heavy rainfall and very strong winds. And sometimes during the summer, we have very intense thunderstorm. They will produce fresh floods. During the winter, we have facing cold surges. The challenge also are droughts because there's a lot of rainfall, but we do not have enough reservoir to reserve water. Therefore, we some years we do facing drought problem. Sorry. And this is a track plot for the maybe last 10 years from 2005 to 2014. About a quarter of the typhoons we issue warning or they actually passing by either over Taiwan or in the nearby ocean about 100 kilometers from the coast. 21 of the tropical cyclone actually make central rainfall. Therefore, the typhoon forecast is one of the top priority job for the Central Weather Bureau. The global warming, which is not exception at Taiwan, is a 100-year surface temperature from early 1910 to 2010. The temperature rising is about 1.630 degrees, which is about twice of the average warmings. The warming particularly increased during the last 30 years. This diagram on the right shows that the red one is a 100-year temperature increase. The green one is the last 30 years. Therefore, the last 30 years, the temperature increase is larger than the previous, especially in the west side of the high mountains. For the temperature change, this diagram shows the torrential rainfall days anomaly. The torrential rainfall is defined by the daily rainfall is greater than 200 millimeters. It's not big change during the 100-year period, but if you look at the last 30 years, the torrential rainfall day is a significant increase during the last 30 years. And this diagram particularly shows the last 30 years, the top 20 extreme heavy rainfall typhoons actually occur during the last 10 years. There are more than 8 typhoons during the past 10 years, and this is extreme cases for Typhoon Morak. The 3-day total rainfall is more than 2,050 and 2,500 millimeters. And this typhoon actually caused more than 600 people lost their lives. This diagram just shows you the Center Weather Bureau, maybe similar to your home country, that we have installed many observation facilities to monitor the weather. The red dot over the island and the blue dots are the automatic weather station and the rain gauges. We have quite dense distribution of the automatic weather station. The average distance is about 50 kilometers. And we also deploy buoys around the ocean nearby Taiwan, and also some tidal station and others. We have installed 6 radar in Taiwan, show here. And we're going to have another 5 C-span radar in the next 3 years. The distribution is similar to this diagram shown here. I like to thank the government of Japan and the Philippines here. We actually can have the real-time data from Iskaki Island, the radar station, and also from Basco and Aparia from Pagasa, which can extend our monitor area further to the east and to the south, which is very important for the weather monitoring at Taiwan, because most of the severe weather during the summertime come from either from the south or from the east. So with those real-time observation radar station from GMA and Pagasa actually very helpful to the Central Weather Bureau. Similar observation may be also used in your home country, including the geostationary satellite observation and the polar orbiting satellites. Others are the Chinese Taipei also provide Formosa, or the term you may be more familiar with are cosmic satellite observation. All those data have been integrated to for our numerical weather prediction usages. And the newly launched Himawari 8 satellite observation also are ready for the Central Weather Bureau to operation. Central Weather Bureau actually perform the typhoon civilian drop zone observation. Those are the some of the dots here are the drop zones we deploy for different typhoons when they move close to Taiwan or be threat to Taiwan. This diagram are pulled from Dr. Yusinini who explain the different service here using different product in different time scale and with some kind of uncertainty. I just put the models the Central Weather Bureau provide to guide our forecast. For 2 weeks beyond, maybe related to more to climate services. Today I will mainly go show you some of the model here for the weather forecast or daily or even hours of the weather forecast. We have a global model also called GFS, which provide a weekly forecast. Similar model also for the climate outlook studies. And we have a version of WOLF model, which is a community available regional model are operated at the Central Weather Bureau, and some of the models are using for short-term weather forecast. I will go through those during my talk. This Central Weather Bureau is kind of fortunate to have the computer hardware just upgraded last month. Actually, we just accept the installation of a new computer system, which is a penta scale of the system, which provide the Central Weather Bureau about 90 times of the capacity compared to the previous generation of the HPC, which installed in 2011. The Central Weather Bureau has the new global model ready and will be operational start in next year. Our previous model is have a resolution, global resolution in 40 kilometer in 40 layers, and with some detail showing here are the configure of different model physics. We just improved the model to 25 kilometer in globally coverage, and the layers in vertical also increase to 60 layers. Some of the model physics are keep the same. For example, this in red one are the physics we upgraded. And we also included the gravity wave track, non-orographic effect of the gravity wave track. And this just a slide to show you the improvement of our global forecast model. Over this side, they are the anomaly correlation for the model forecast, which is 1 is the perfect one if the value is close to 1. And the red line are the new model, and the black line are the previous operation model. You can tell from this diagram that the new model actually is improved quite significantly, particularly in the upper atmosphere. And this diagram just show you a example of the track forecast for Typhoon Suda this year. The red line are the best track, and the blue lines are different forecasts starting from different initial time. This is the current operation model, and this is our new one. You can tell from this diagram that some of the forecasts here have the right-hand side errors, but those errors are decreased and more accurate from this higher resolution simulations. And this is also a diagram to show you the improvement sorry, this is a mesoscale. I maybe like to do the regional or mesoscale forecast. The Central Weather Bureau has installed a WRF-based system from 2007. It's almost 10 years after now. After we installed the model, we currently the model domain are showing here. We have a coast resolution in 45 kilometers, cover a large area of Asia, and we have a domain with 15 kilometers centered in Taiwan and cover a portion of Philippine Islands, and a fine resolution in 5 kilometers just cover the area of Taiwan. And some of the detailed phases I will skip this. And for this model, we produce 4 times per day for deterministic forecast. We also have the 20 members ensemble prediction from the same model with 4 times per day. And this diagram just shows you that the error has been reduced during the past 5 years. This for 2010, 2011, and that is 2014. The error for the 850 hPar temperature, the error actually is reducing. Similar for the geopotential high forecast, showing the model has been improved. The improvement actually has been, many activity have been studied at the Central Weather Bureau, try to improve the model. Some are adopted from the community, the WRF community. Some are, thank you for the NCAR United States. We have very close collaboration with them, and some are in-house development. Some of the studies are in model physics, including radiation skin, the cumulus skin, and the surface processes. Also, some activity are trying to have better initialization, and actually the Central Weather Bureau finds some bugs and fix them with the collaboration of NCAR, the model developer. And we spend quite an effort trying to have better data assimilation. I will not go too into the details. But I'd like to show you here is our ensemble system. Later, several speakers will come to the ensemble forecast. Our ensemble system for the regional forecast are using, as I mentioned, the WRF model. The domain coverage is like this. We perform 4 times per day. The perturbation come from 3 different subjects. One is from the initial random perturbation, and we also perturb the later boundary, and also using different model physics to have to compose those ensemble. And this diagram just shows you the dispersion relationship for the ensemble. If you have the dot in the diagonal line, they will have a perfect ensemble model. Our model is still not perfect yet, but it's meaningful from the model product. This is just an example to show one of the ensemble forecast for the actually there are 24 members. 20 of them are come from the ensemble system. Another 4 are come from deterministic forecast. That's are the observation during the particular event, and those are individual forecasts for the rainfall forecast. Some of the members do look like the observation. For example, this one actually captured the heavy precipitation at the northern part of Taiwan. Some of the examples, they capture also the heavy precipitation at central Taiwan. But because the model initial field are perturbed, therefore some of the model do not have those intense rainfall from the member for predictions. Actually, we found that if they just using the simple mean from all the members, the extreme rainfall be smoothed out due to the average process. For example, this is the observation for this particular event, and those four diagrams are different. There's a 12-hour forecast, there's a 24-hour forecast, there's a 36-hour forecast, there's a 40-hour forecast. Most of the forecasts have the information they're going to have some rainfall, particularly at the northern or central portion of Taiwan, but those very heavy rainfall or the rainfall extreme are reduced from the simple averaging from all those members. This is a case of the stationary front or the main front cases. This is the case from a typhoon rainfall. And these cases are not a very strong synoptic forcing circumstance. This only a very local, very intense rainfall, very small scale. And actually, the model able to capture those potential, but the amount of the rainfall are in general underestimated for the extreme rainfalls. And this diagram have a better idea to show you the mean of the ensemble prediction system from the single average is less than the observation. This diagram is a occurrence probability in the vertical axis, and this is from different rainfall. This is about 100 millimeter per 12-hour rainfall event. The black line are the observations. The blue one are the simple average from the ensemble. So over this area, the observation and the simulation or the model forecast probability distribution are quite close. But over this part and over this part, this area are the very light rain area. Due to the average, you will increase the light rainfall, but will reduce the intense rainfall from the mathematic average. To improve this, the Central Weather Bureau applied so-called probability matching concept. This probability matching just assumes that all the members together will produce a similar probability distribution as the observation. So I will not go into the detail of the step we're using to apply this probability matching, but just show you that after apply the probability matching, which is shown here are the green lines here. So the green line is close to the observation compared to the previous, just a simple arithmetic mean. And this is another diagram to show you for the study of of a 1 year May season, that's a station from May to June of last year. This is the equitable threshold. The number larger is the beta forecast. The green line, actually the probability matching method applied here are shown here by the red lines, and the simple arithmetic mean are shown in the blue line here. I will skip others, just let you see that for the very light rainfall, the improvement is not that much. But for the heavier rainfall, you can tell from this diagram the probability matching method have the larger value, which means the both beta forecast than the simple mean here. And this is just show you cases. This is observation. This is a simple mean by average, and this is the apply the probability matching method. You can tell from this diagram that some of the extreme can be recovered from the probability matching method. Actually, we found some of the overhead forecast, so we have developed another probability matching and can further reduce the errors. This diagram just shows you that some of the efforts are taking place at the Central Weather Bureau try to have better data assimilation. I will skip this because there are too many details. Just come to the typhoon track forecast. This diagram shows you the track forecast error in the vertical axis during the past maybe 7 or 8 years, starting from 2008. And this one is for the 24 hours track forecast error. This one is for the 48 hours forecast error. This for the 72 hour. The dash one or the dot one are our official forecast, and the solid line are our model forecast. So during the last few years, actually the model can produce quite good forecast comparable to the forecast, the official forecast. I think our official forecast is very similar to the leading forecast center, particularly less than 48-hour forecast. And down here are some activity we have applied to reduce the forecast error. I just like to mention here are the two-way interaction updates taken this year. Previous version of the WRF do not include the two-way interaction nesting. The information are passing from the coarse resolution to the fine resolution model by the data boundary condition. They do not passing out the fine resolution result to the coarse resolution model. Therefore, there's only one way to improve the model. A two-way nesting are developed at the NCAR, and the Central Weather Bureau apply those new feature and to study whether this new feature will improve the forecast. We have finished a 11 tropical cyclone simulation or the test with the two-way interaction. The blue line here and the light blue line are the previous version or the one-way interaction forecast error, and the red one is the model with two-way interaction. the error is significant in decrease, particularly for the coarse resolution domain. For example, for the 72-hour forecast, the original model had about 200 kilometer forecast error. Now it's reduced to about 170 kilometers. And this is just an example show a particular case of tropical cyclone Feng Wang. The base track are shown here by the solid black line, and all those red lines are forecast from the simulation from the model. From here, you can tell there's quite large forecast error for the previous one-way interaction model, and those errors are reduced by using the two-way interaction model. For the tropical cyclone rainfall forecast, the simple ensemble for the front system is not able to apply successfully for typhoon track forecast, because we found that the tropical cyclone rainfall are significant depends on the tropical cyclone location. So if a model do not have the track center forecast good, then they will produce a large forecast error. Therefore, we try using a different approach to using the forecast center as a parameter to choose the ensemble average. If we have an official track forecast error, have the center here, then we just select all the previous forecasts from the model with the forecast center are nearby the official center location. By using this approach, actually they produce quite good forecast. This is three cases from this year. The rainfall observation like this, and our model forecasts are look like this. Actually, the model able to capture most of the significant rainfall area during the tropical cyclone invention. And also by using this approach, we also able to assess the uncertainty of the rainfall from different track. If the track moving more close to Taiwan, then for this case, they will produce more enhanced rainfall over the east part of Taiwan. And for shorter range forecast, particularly focused on 0 to 12-hour forecast, the Central Weather Bureau had introduced a lab system for NOAA about 10 years ago, and now we update it to a system called STMAS. This system actually able to produce a small scale and more rapid update cycle. This system has a strong point on the analysis, because the analysis scheme was able to include variety of the data set into the analysis for the forecast. Particularly, they have the cloud analysis scheme. They will have the cloud base or cloud top or cloud fractions after the analysis. With those complete cloud information, the forecast model can minimize the so-called the spin up problem. They can produce the rainfall during the early stage of the simulation or the forecast. And this is just a diagram to show you that the forecast from 0 to 3 hours, that's 6 to 9 hours, that's a different period of the forecast. And the blue one is just called the STMAS world forecast. And the red one is our ensemble forecast. And from this diagram, we can show that during the early age of the ST mask can provide better forecast for short range forecast. And also for the thunderstorm, because the thunderstorm also produce very heavy rainfall, they will have flash flood. We have the auto nowcasting system just installed it. And I will show you just an example. I will skip the detail of the model and just show you we have to study and to find the predictors from the data analysis. And this diagram just show you the factors, the predictor we found it's important to the thunderstorm forecast. And this diagram show you some blue one are the actual observation, and the colors here show the likelihood of the initiation of the thunderstorm for 1 hour forecast. You can see from here, actually the model predict they're going to have thunderstorm, and actually later they do have some thunderstorm. But this area they are over forecasted, and this is a similar case but a later forecast. They show quite good of the spatial and the temporal distribution of the thunderstorm, which is forecast 1 hour before the initiation of the thunderstorm. And for the service, the central weather bureau had distribute the warnings by different way. For example, the short message, the lines, which is also a real-time message application software, and the CWB apps to provide the warnings to different agencies or the publics. And the Central Weather Bureau have provided data over the home pages. If you're interested, you can look at from the website. And the Central Weather Bureau actually customize the information provided to relative government agencies. For example, for the highway or for the railway, they can give in some criteria, then our system will automatically generate the alarm. If the criteria meet their operation, they will start their operation downstream. And the Central Weather Bureau also provide the binary data to different agencies. So for example, the Water Resources Management Agency, they are doing the water resources management and flooding warnings. And also the Central Weather Bureau provide the data to NCDR. They are a colleague from NCDR are here. They are responsible for the supporting of the emergency operation for the central government of Taiwan. Okay, many future work I just left here. I think there's a lot of things we need to do, particularly for the data assimilation, for the model increase the resolution, and more importantly, we have to do more model verification and focus on providing application to different agencies.